Internet of Things refers to billions of physical devices around the world that are now connected to the Internet, collecting and sharing data. For example, refrigerators that can show you their contents on your smartphone. The home heating and cooling systems that can adjust according to the weather report. As it turned out, most Internet of Things devices rely on analog sensors to at least some extent to collect the data that's used for devices' operation. In the most case, these analog sensors are integrated with an analog to digital converter which translates raw data into digital form. Delta Sigma ADC has commonly used converter in IoT devices. These analog to digital converter provide high-resolution digital output instead of high conversion speed. A Delta Sigma ADC always consists of a Delta Sigma modulator which produces the bit stream and a decimation filter. Besides, Delta Sigma ADC uses oversampling frequency to the clock which allows noise shaping and anti-aliasing techniques. Cascaded integrator comb filter was first introduced by Eugene Hogenauer in 1981. It is a simple architecture and multiplier-less low-pass filter which built from delay element and full adder. In fact, CIC filter composed of integrator stage and comb stage. The two interchangeable stages can be implemented as decimation filter or interpolation filter. Our team proposed two methods to improve power consumption of CIC filter. First, we focus on delay element architecture. A conventional delay flip-flop is compared with true single-phase clocked TSPC-D flip-flop. The TSPC-D flip-flop made out of only 8 transistors where it only covers smaller area and low power operation. We focus on the full adder architecture in method 2. 4 different static full adders are implemented into CIC filter for performance analysis. A conventional static full adder consists of pull-up and pull-down network that made out of 28 transistors in total. A pseudo-NMOS full adder replaced pull-up network with 2 PMOS. A 16T hybrid full adder can be represented by 3 independent modules. 14T hybrid full adder modified the module 1 of 16T hybrid full adder to reduce 2 transistors. The Siltra 130 nanometers CMOS technology were used to simulate the CIC filter by using mental graphic. In the first method, the power dissipation of CIC filter integrated with TSPC-D flip-flop has reduced significantly from milliunit to microunit. If compared to previous works, the TSPC-D flip-flop can be considered as low-power implementation within CIC filter. In post-layout simulation, the average power consumption of single-bit CIC filter is 2.82 microwatt where only increased 0.5% from pre-layout simulation. In the second method, the 4 architectures of static full adder were implemented into CIC filter to compare the performance by varying supply voltage from 1 volt to 1.4 volts. Graph of power consumption against supply voltage. Graph of propagation delay against supply voltage. Graph of power delay product against supply voltage. The 16T hybrid full adder CIC filter has improved 38% overall performance compared to the conventional full adder. In post-layout simulation, the average power consumption increased 9.55% from pre-layout result.